polynomials and symmetric tensors, but they are a result of some insights that I did have when I was working through this year. So here's generally how my talk is going to go. I'm going to go over what symmetric tensors are, just because I'm going to need some of that terminology. I'm going to go over some graph terminology, and specifically I'm going to introduce the graph integering of varieties. And that's why I'm working with graphs in the first place. And then I'm going to try and attempt two distinct results. Right? One is going to be, can I take the grading from symmetric tensors and homogeneous polynomials and transfer it to the world of graphs? And then on the flip side, I know that graph polynomials have some interesting properties. Can I move those properties to the world of symmetric tensors? Right? So what is a symmetric tensor? That's my goals for the presentation again. The closest paper that I found in all of this, especially trying to figure out are graph polynomials related to symmetric tensors, this paper by Cruikshank from 2024, where they related graph rigidity to symmetric tensor completion. And while that is technically a paper that relates graphs to symmetric tensors, that wasn't exactly what I was looking for, because they still were using distance. And I don't care about the distance. I just care about the structure of the graph, so to speak. So the topological properties of the graph, not necessarily the distances, right? So those are my two attempts, right? And spoilers, I am not going to be able to say anything about either putting a graded structure or about making a Berkeley-Brosnan type result on symmetric tensors, right? But I will show you the attempts anyways. So what is a symmetric tensor? This is a classic physics definition, physicists in the room. If they transform like a symmetric tensor, they are a symmetric tensor, right? But in general, if I have let's say, D vector spaces over a field K, then my tensor product is a multilinear, or represents a multilinear mapping from the dual spaces V1 dual times V2 dual times to VD dual to the underlying field, right? If I have a symmetric tensor, all I'm saying is that under the symmetric action, where sigma is my symmetric action here, the tensor is invariant. So especially if I look at the action on elementary or rank 1 tensors, then the symmetric action doesn't change my tensor, right? So some notation, V to the tensor D denotes the tensor product of the vector space with itself D times. SD, the space of all symmetric tensors, is a subspace of this larger space, right? And my elementary symmetric tensors are going to be of the form small v tensor itself D times, right? So we've seen this covered before. I think Matteo covered this as well, which is what is the relationship of symmetric tensors with homogeneous polynomials. So there is a result in the literature that says that if I take my homogeneous polynomials of fixed degree in a polynomial ring, then I have an isomorphism of k vector spaces between the homogeneous polynomials of fixed degree and symmetric order D tensors, right? And specifically, this is given by linearly extending the mapping of monomials, right? And in particular, I want you to notice that the mapping of each monomial is to symmetric tensors, and it looks like an ugly expression, but that essentially captures why these are going to be symmetric maps, right? Now, that's the algebra bit. How do I look at it in geometry? So if I take now PV to be the set of all lines in a vector space passing through the origin, then the classical Veronese mapping allows me to take points from PV and map them to a Veronese variety, right? And these basically allow me to talk about elementary symmetric tensors lying on a variety in some pk, where a pk to the n, where n is given by choosing d elements out of n with replacement, right? And so that's essentially all about symmetric tensors, how I can see them algebraically, how I can see them geometrically, where the graphs come in. So I'm going to introduce some graph terminology, right? So I'm taking a graph, I'm saying that it consists of a vertex set and an edge set, and I'm saying that the order of the graph is the number of vertices, the size of the graph is the number of edges. I'm interested in B naught of G, the 0th Betti number, which tells me how connected the graph is. and B1 of G counting the number of loops in the graph. And B2, B3, higher numbers or higher topological indicators don't matter to me. So these are the two important ones. A tree in a graph is so a tree is a connected graph that is connected and it does not contain any loops. If I was asking about a graph, or if I was talking about a graph with had a B naught higher, I would say forest, but I'm just going to focus on trees. Particularly, I'm concerned with spanning trees. So spanning trees, I'm going to denote with the less than or equal to sign. So a spanning tree that lies inside a graph contains all the vertices of the graph, but it does not contain all the edges, right? And specifically, I want it to be a tree. So if suppose I had, like for the simplest example, if I have a graph with 4 edges, my spanning tree only contains, let's say, 3, and I have at least 4 spanning trees, right? So now, because I know how to construct spanning trees, what I can do is construct graph polynomials. And in particular, I'm going to focus on a particular class of graph polynomials called Kirchhoff polynomials. So for the rest of this talk, I'm fixing the number of edges of my graph. So the size of my graph is always going to be n, and n can vary, but it's still n. And the number of loops of my graph are important, but my graphs are always connected, right? So a Kirchhoff polynomial I can define as summing over all the possible spanning trees, and then I can take the product of edges that are not considered in the spanning tree. So for this graph in particular, if I have to calculate its Kirchhoff polynomial, I can, if I label my edges x1, x2, x3, and x4, then the Kirchhoff polynomial associated with this graph is essentially just going to be x1 plus x2 plus x3 plus x4, right? Because I'm just counting the edges that I'm excluding and then summing over all spanning trees, right? So that's how I construct my Kirchhoff polynomial. And this polynomial, it does not matter how I label my graph, because I'm summing over all spanning trees, regardless of labeling, I'm going to get the same polynomial. There's a caveat that I will introduce in a bit, right? So where do these polynomials lie? So these polynomials lie not just in now the ring, this quotient ring, where my n comes from the size of the graph, but it's also quotiented out by these square terms, because I'm never going to be counting edges twice, right? Interestingly enough, the degree of my polynomial is exactly the number of loops in my graph. And so now here's the caveat. I said relabeling didn't matter. Suppose I had, let's say, a graph of now size 5, right? And I add an extra edge there. This term, if I label this x5, gets mapped to this polynomial now. So x5 times this linear polynomial. So anytime I have self loops, I get these terms that are common, that always get excluded. So now what I can do is I can also now write an equivalence relation based on the relabelings, right? Where I can say graph polynomial A is related to graph polynomial B, if and only if they're similar up to switching labeling of these edges around, right? And so this is how I get Kirchhoff polynomials, and they seem interesting, but why do we care, right? And so this is why I have to bring in the Grothendieckring of varieties. So VK in the literature is considered to be the category of geometrically reduced separated schemes of finite type over a field K. I'm just going to consider them as K varieties. That's what they usually get referred to in the literature as well. So I'm just going to call them K. This is the space of all K varieties. Now, if I can partition VK by equivalence relations, so in this case, the equivalence relation is given by x and y are equivalent if there's a birational morphism that exists between them, right? Or birational morphism for the physicists in the room is just a dense subset is isomorphic, right? So if x and y are birational to each other, then I can say that they are related. So k naught of vk gives me this partition, and I can introduce the addition as taking disjoint unions. However, this does not give me a group. I still have to figure out what subtraction looks like in this group. And an easy way to do this, or the way that they do this in the literature, is you mod out all of the relations of the form x is equal to x deleted y plus y, where y is now a closed subvariety of x. And doing this, it seems like a hack. Doing this basically allows you to talk about subtraction. This allows you to write kvk out of k naught vk, and this kvk forms a finite free additive abelian group, which is the Grothendieck group of varieties. If now you define multiplication by taking the fiber product, the class of the fiber product, you now have a commutative ring with unity. And here the unity is the equivalence class of a point. Right? So now we have the Grothendieck ring of varieties developed by Grothendieck. Kontsevich uses this in the 90s to start doing motivic integration, and motivic integration is useful to people, right? And KVK is now, since it can be seen as a module because it's a ring over R, it's a module over Z, but it can be specifically seen as a module over ZL. And here L is the equivalence class of the affine line. For people familiar with motivic integration in the room, that is the Lefschetz motive, right? So why do we care about the Grothendieck ring in relation to graph polynomials? So Belkin and Brosnan in 2003 start by first saying, let's look at the zero set of these graph polynomials in affine space and take their hypersurface complement. So I'm looking at YG defined as AN deleted the zero set of the graph polynomial. Belkin and Brosnan show that if you take a particular multiplicative subset, then suddenly what you can do is say that the localized Grothendieck ring is generated by all of these graph polynomials as a module over S inverse ZL, right? And that's quite interesting because graph polynomials suddenly are generating this entire ring, but they're a really small part of this ring. So is this something that's going to hold if I don't localize? Is it going to hold if I don't consider it this is a ring over S inverse of ZL? If I remove L, does that change anything? And unfortunately, yes, this localization is specific. So in 2001, Larson and Luntz showed that if I mod out by the Lefschetz, the ideal generated by the Lefschetz motive, suddenly I have an isomorphism with the ring of stably birational varieties. And then Alufi and Marcoli in 2011 show that, listen, if we do take the Grothendieck ring and we remove the or we mod out by the ideal generated by the Lefschetz motive, suddenly these graph polynomials don't really matter. You only get the integers in this specific ring. So clearly this Lefschetz motive matters. And further, Alufi and Marcoli also show in their 2011 paper that the localization matters, right? Because if you perturb the localization slightly, in the previous localization, a common factor of L, if now I take out a common factor of L, suddenly I don't get a generating behavior from these graph polynomials. So that's quite interesting. And so my question then was, is it possible for these graph polynomials, since they are homogeneous, and since homogeneous polynomials are isomorphic to symmetric tensors, is it possible to have some sort of generating behavior in the symmetric tensors? And then vice versa, is it possible for me to get a grading back to graphs, right? So I'll tackle the first question. Could I get a grading on graphs, right? So if I take Gn to be the family of all connected graphs with fixed size n, a fixed number of edges, then my corresponding graph polynomials, as I've said before, lies in this quotient ring. In particular, I'm going to consider this ring over the finite field of only two elements, right? So only 0 and only 1. This makes addition easier for me, right? If I do so, then I can now look at the equivalence or the partition of this set by both graphs that are equivalent if they have the same Kirchhoff polynomial and if they have the same Kirchhoff polynomial up to really big. So if I do this, then I get a nice partition of my set, and then I can write it as a disjoint union based on the number of loops each graph has. This is nice. Does that mean I can also start doing addition now? I can attempt to do addition, right? So if I take two equivalence classes, then so if I take A and B, then I can take their corresponding Kirchhoff polynomials. The corresponding Kirchhoff polynomial classes look like this, right? Up to symmetry. And adding these classes gives me a set of this form, right? Where I have P and Q, where P is related to PA, Q is related to PB. And I can, because I'm working over F2, I can find an element with the largest number of summands, right? These are finite sets, so I can find a largest or multiple largest summoned elements. The question then becomes, is this polynomial that I have found, can it be mapped back to a graph? And that I'm going to say is a conjecture. That is a very bold claim for me to say, but I'm going to say that it is a conjecture, right? Because I don't know if this polynomial can be mapped back to a graph. But if I can do so, then GN does become an additive billion, right? And that's an additive. I'm trying to establish an additive structure on the space of all graphs. On the flip side, now let's go to, can I do a Berkeley-Brosnan type result on the space of symmetric tensors? So then my question, so R describes a quotient ring, which does induce images in, so representatives in homogeneous polynomials. And these are definitely not elementary tensors. They're not elementary tensors simply because all of these are going to be of mixed form. I will never have a polynomial with an exponent larger than 2, right? So these are definitely rank at least D tensors for D loops, right? So since none of these can be represented as polynomials to the dth power, they don't lie on the Veronese. Can I show them as lying close to the Veronese then? And here I have made a mistake. It is not a mapping mu d from PV to PK. It should be the mapping, the complement of this set. So V, I went wrong. Yeah, this the complement of this set, right? Just because I don't want any of these mapping to all zeros, right? So if I look at this mapping, the mu d, then I can sort of, okay, I can replace PV over there with this set, right? I'm going to call this X, right? Then I can see these as included more or less in the Veronese surface. And so then my Kirchhoff polynomials are now secant to these images on the Veronese surface, not, right? So I do have now a geometric picture of where these polynomials can lie when I look at them close to the Veronese variety. My next question is, if then graph hypersurfaces can generate the Grothendieck ring localized, can I look at these images in close to the Veronese variety? Can they also generate all possible symmetric tensors? And because every homogeneous polynomial does generate a variety, we know this from elementary algebraic geometry. So every homogeneous polynomial can be mapped to a variety or its complement. So every symmetric tensor can be mapped to a variety or its complement. So in particular, if I map to the complements, I have the symmetric tensors corresponding to the Kirchhoff polynomials. I have them mapped exactly to the equivalence classes of the graph hypersurfaces or the graph hypersurface complements that I had defined earlier. The question then becomes, is there an element similar to A1 in the symmetric tensors, right, under this isomorphism that I have between these classes? And it turns out, no, I don't have an exact relationship. I don't have an exact mapping of the equivalence classes that I find, because I need more than one polynomial. I need to define the intersection of more than one polynomial, right? And that's not a notion that's well established in these two settings. So if suppose I was able to find an equivalence class of the affine line, then potentially the Berkeley-Brosnan result could be done. But since this is not the case, I have to stop here and try and figure out, is there a way that I then induce a topology from the Grafman deep ring of varieties onto the space of symmetric tensors that allows for this result to carry over. And that's my talk. So that's how I would want to reframe this question. So there are further questions, right? So is there more underlying structure to the ring of Kirchhoff polynomials? And specifically, this example of if I have a graph of size 5, right? Because the polynomial x1, x2 plus x3, x4 does lie in the ring that I have defined, but so far I have not been able to figure out what graph it corresponds to, which is why addition also becomes a conjecture for me. So is there more structure to the ring of Kirchhoff polynomials than I had previously thought? Does that also mean there's more structure to the world of graphs of finite size than I had previously thought? And my second question is, I was working over F2. Does changing my underlying field to be K change the way that I can do addition and other operations on the space of all graphs, right? And specifically, I'm thinking of weighting not as direct, so adding my underlying, changing my underlying field as instead of looking at, so the same graph, instead of looking at these as just being counted once, I'm looking at these taking values, let's say alpha 1, alpha 2, alpha 3, alpha 4, where they lie in the underlying field. Maybe that's a way to improve what I've been doing. But those are my questions. And yeah, if suppose a Berkeley-Brosnan type result does exist for symmetric tensors, if I can port it over, then what does that mean for symmetric tensor decompositions or the lengths of symmetric tensor decompositions? Is that a definitive upper bound? Is it not? But yeah, those are the questions that I had at the end. So that's my talk. These are my references. Any questions are welcome.
You mentioned this word called rigidity at the
Yes.
beginning. Like I lost the connection of this word.
So the work by Cruikshank does relate graphs to symmetric tensor completion. So from what I remember of their paper, they take a graph, an arbitrary graph, they take a distance metric, and they look to first generate a symmetric tensor that represents this graph, and then they want to see if the symmetric tensor does not contain as many values as they need. How do they complete this tensor? If the tensor, when I say it's not complete, I mean there are entries that are unspecified. They look to see if you can complete the graph while still keeping the symmetry condition, because that corresponds to rigidity, in as much as I've understood from that paper. Yeah. Mm-hmm.
Tensors would be graphs.
Mm-hmm.
Yes.
Yeah. Okay. Yeah.
What is the relation?
So that was the closest paper I found relating graphs to symmetric tensors in this format. I still didn't see a relationship between the polynomials that I needed, so these polynomials, Kirchhoff polynomials, and symmetric tensors. Those papers, the closest thing I found to talking about Kirchhoff polynomials was papers about heat kernel transfer, where these are called Symanzik polynomials or first Symanzik polynomial as well, but nothing relating these polynomials to graph tensors, because that connection is well established, at least for the mathematicians. But then from here to there, I hadn't found anything. So, yeah.
Good question.